and share my screen. And so we'll go ahead and get started for today, June 11th, 2021. But where we left off on Wednesday was really just looking at constitutive relationships, that relationship between stress and strain. We defined earlier that stress is a tensor. And here strain is also defined as a tensor and can be drafted in matrix form according to the following matrix. The only thing that's slightly different with your strain matrix is that when you're looking at the constitutive relationships, you have your principal strains, epsilon x, y, and z across the diagonal. Instead of having your shear strains directly, for the other values, it's actually half of those values. So it's the shearing strain divided by 2 that will appear in those cells in the matrix. That's just the consequence of how that constitutive relationship develops between stress and strain. And so that's something always to be aware of if you are just looking at a matrix of numbers for the strain matrix. Always remember to multiply the number that appears in the cell by 2 to get the actual shear strain. And so that's the main thing to be aware of when looking at the strain matrix. And again, that can be derived when looking at equilibrium and compatibility for a differential element, and that constitutive relationship between stress and strain. And so from different analysis perspectives, kind of what we looked at on Wednesday with axial loading, direct shear loading, we're really just drawing a free body diagram and seeing what the internal force is, calculated an average stress. And so that gets to be more of the mechanics of materials approach down below. A higher order level of evaluating that is really looking at the theory of elasticity that Timoshenko developed. With this, both equilibrium and compatibility can be defined in terms of partial differential equations. And so when you look at a differential element and really show that stress and strain can vary as a function of position and derive that, essentially your summation of forces and moments to account for that, that'll generate a PDE that you can solve. And so normally, like when you take Math 321, you're looking at ordinary differential equations, which are a little bit easier to solve. When you get into partial differential equations, there's more complex solution methods to solve for those. And so that tends to be more of a focus of graduate studies when you look at the advanced engineering analysis, getting into PDEs. One of the benefits is a lot of these common type problems dealing with the theory of elasticity have been solved. And so they show up a good resource is ROARC's formulas for stress and strain. And that's been revised and updated by Warren C. Young. My guess is they may have a newer version down at the library, the Devereux Library, but this was the version that I saw and was using a couple decades ago. They update that periodically like they do most textbooks. But I think from that standpoint, that's a good resource if you're dealing with kind of a common type problem and you want a theory of elasticity solution. You may find that in general form in RoArc's textbook there. And those are all set up in terms of relationships with respect to variables so that you can put your geometry variables, your material properties, and all that stuff in there to determine what displacements might be, what the state of stress might be. For our undergraduate curriculum, we really do focus on the mechanics of materials approach, where we really look at structural elements and analyze those as idealized models, looking at the basic axial loading, torsional loading, bending, transverse shear, things like that, so that when we go through the design process, if we kind of constrain the system to be very close to those idealized models, the mechanics of materials approach provides an adequate approximate solution so that you can design a structure safely. But then that approximate solution, that's really obtained by algebra, calculus, and ordinary differential equations as opposed to partial differential equations. And I think when we start getting into things like column buckling and beam bending, associated displacements with that, that's when you get into calculus and ODEs a little bit more. So we will get into those here a little bit later in the summer. But it's pretty straightforward. I'll take you through the process of essentially integrating back through, looking at the constants of integration and solving those via your boundary conditions. And it's just a process to go through to solve that stuff. One nice approach too, with all these analytical methods, is to have verification throughout that process. And so if it is very simplified, you can get by with just doing a mechanics of materials approach. But if it starts to get more complicated in terms of the loading conditions, geometries, things like that, the mechanics of materials approach is still a nice method to get really just an order of magnitude estimate on what the state of stress is, what the displacements are. You're making simplifying assumptions to do that, but at least you have a ballpark idea of what the state of stress is, what the displacements are. And so then if it's concerning, then you can go on to say a theory of elasticity approach that's more accurate. So you can get a better idea of what those states of stress are, states of strain, displacement. And then with that being a more complex solution method, if you are still within that ballpark order of magnitude from your mechanics and materials approximation, you have a little bit more confidence in your theory of elasticity solution. And then the third method is computational methods, where you do that analysis numerically instead of with the analytical tools that we have here. So the finite element method, finite element analysis, is really that main tool then to do a computational analysis. And there again, it's ideal to do that verification. What you're really doing with that is, again, attempting to get an approximate solution for that complex state of stress. And that you can compare back to a theory of elasticity solution if it's available, or at a minimum, comparing it back to a mechanics of materials approach just to make sure that you're in the ballpark. That's my biggest concern always when you undertake a finite element analysis, is that it is easy to make a model and put loading on it, boundary conditions, and get nice numbers and figures out. But if you've put incorrect information in anywhere in that process, those numbers are not going to be accurate. And so with your finite element analysis, you really need to have some way to verify those results are accurate. And you can do that experimentally to measure that. You can also compare it back to mechanics of materials approximate solution or theory of elasticity solution. So always take that into consideration for those of you that do stress analysis in the future. The same thing applies if you're doing fluid analysis or heat transfer analysis. Really that need to do verification. And the nice thing is that finite element analysis, you can really apply that to the structural analysis. You can apply it to heat transfer and fluids. So it's really a nice tool that can be applied across all a lot of the different disciplines here in mechanical engineering. You're getting close to choosing your senior electives for the coming year. I think FEA is probably the senior elective that I've used the most throughout my career, just having that fundamental background in that computational method. And so now we'll get into chapter 4 of Hibbler, looking at the axial loading conditions. And really it just combines concepts that was learned previously in chapter 1, 2, and 3, where chapter 1 we learned that stress sigma is equal to a load P over the cross-sectional area for an axial loading condition. Chapter 2, we learned that axial strain epsilon is equal to the displacement delta over L. And in chapter 3, we learned the 1D Hooke's law. Sigma is equal to the Young's modulus times strain epsilon. And then we also learned the full 3D Hooke's law, but chapter 4 just deals with pure axial loading. And with that, you can use 1D Hooke's law. And so essentially chapter 4, all it entails is making those substitutions into your 1D Hooke's law, P over A for stress, delta over L for the strain. And you can then rearrange this to solve for the corresponding displacement, PL over EA. And again, this applies for a uniform axial member where the load, the Young's modulus, and the area are constants over the section considered. If you have variable cross-section or loading, that type of thing, then this would collapse. It would expand into an integral expression that you'd have to do to solve for that resulting displacement. For all these things constants, it collapses down into this form. And so the non-uniform axial deformation, where we have the integral term, we can consider an axial loaded member where the load, modulus, area are all functions of x along the length of the axial member. And so that displacement then would be each of these is a function of x, p of x. The Young's modulus is a function of x. If the geometry varies along with x, all those are just all functions of x. And so the displacement would be that integral with respect to x and putting in the limits of integration from 0 to L. And so again, E could be a function of X due to functionally graded materials with laser powder deposition. You could have that axial member start with aluminum on one end, transition to an aluminum titanium mixture, and then be titanium all the way at the other end. So you have the power to really adjust the Young's modulus as a function of position. That's not commonly the case. Generally, you're buying raw material and making a component all of the same material. But there is a possibility that that could occur. When you are generally dealing with segments, if you have segments of different materials, those really can be looked at from each individual member separately, and then looking typically at the compatibility. One is going to want to maybe stretch more than the other. They're kind of working against one another. And so based on the Young's modulus of them two materials, where is that equilibrium point where equilibrium is satisfied? And so we'll have a few example problems here. But I think for your basic problems, you really likely covered those in ME 216, where you're dealing with statically determinate type systems. And so we'll just have one example in relation to statically determinate. That means that if you draw a free body diagram, you would be able to see what the internal loading is just from the free body diagram alone. Statically indeterminate, you need to make use of compatibility. For this one example, we're just given a 30 millimeter diameter steel rod that has a 1 meter length, and it's attached to a mono nickel alloy. Its Young's modulus given a tube here. So these are both circular cross sections. The tube has a 40 millimeter inner diameter and a 10 millimeter wall thickness. Be really careful when they say things like that, a 10 millimeter wall thickness. We have to add that on both sides. So that would make for an outer diameter of 60 millimeters. And it has a 2 meter length overall. And what we're asked to find is the load P that is required to stretch the assembly 3 millimeters. And so one thing that I did, I guess I did do it. I did that last year to show students. I normally just did this on the board. So I got the notes updated, but we'll just show the diagram. Again, we have a load on each side. We have the steel section on the left. We'll call that 1. The mono nickel material 2 on the right. Lengths, diameters, all that good stuff. And there's just a rigid plate that couples the two together. And so the nature of this project, or this of this problem, is that this load is being applied, and each one of these are going to stretch in that process. And so we're looking at that total displacement, the sum of each one of these displacements equaling to 3 millimeters. And so the units that we'll use, force in newtons, length in millimeters, and Young's modulus in megapascals. And then if we maintain that, maintain those units, everything will work out properly there. But I did draw a free body diagram of section 1 just to show you how easy that is. If we make a cut through where the 1 is located, there would just be an internal force acting and away from the cut. Again, remember our positive convention. And so if we sum forces in the x, we just have an f of I minus p equal to 0, which tells you that the internal force there is just equal to p. And so I think the free body diagram is helpful because sometimes students will see that there's a load P on each side and they'll think, well, internal, it has to be twice that, 2P. But when you draw a free body diagram, then it's clear that that internal force is just equal to P. So you can always rely on your good friendly tool of the free body diagram to determine those internal forces. And so that's going to be the same for section 2. If we were to make a cut, we'll just see that that internal force is P. And so what we're solving then is the total displacement being 3 millimeters. And that's really just the sum of the displacement of our steel section plus the displacement of our mononickel section. And we can make use of our displacement relationship where the displacement for the one is just P L1 E1 over A1 plus P L2 E2 over A2 will give us the total displacement, and we're wanting to set that to 3 millimeters. We can calculate the cross-sectional area of each section. Remember, pi r squared is the radius. If we plug d over 2 in for the radius, that becomes pi d squared over 4. And so the area of the steel is pi times 30 squared over 4, a little over 706 millimeters squared for the first section. And then for the mononickel, since it's a tube, it would just be pi times the diameter outer squared over 4 minus pi times the inner diameter squared over 4. And again, outer diameter is 60 millimeters and inner diameter is 40. And we end up with an area a little over 1,570 millimeters squared. And so then with this, we can pull P out of the right-hand side and then just put in our various values of our lengths, 100 or 1,000 millimeters, our Young's modulus of steel, 200,000 megapascals, and that area we just calculated, plus 2,000 millimeters for the length of the mononickel, its Young's modulus and area we just calculated, and all that's equal to 3 millimeters. So we are all set now, one equation, one unknown to solve for P. And when we do that, we end up with 212,000 newtons with our force being in newtons, and we could then convert that to kilonewtons if you wanted to shorten the number of digits you have in your answer. Generally, as you're going through and solving these types of problems, you'll want to carry like 4 to 5 significant figures through your calculations, but then it's fine to round your final answer off to say 3 significant figures. But if you were to round 3 significant figures throughout, as you're solving that, you'll end up having truncation errors where your final answer could deviate by a bit because you're rounded off in the process. I guess any questions so far? And that was really, again, stuff that you would have done back in ME 216. And then as we move on, looking at statically indeterminate axial loaded members, the problem that we run into is when you draw your free body diagram, you can only do your summation of forces and summation of moments. And that'll give you a given number of equilibrium equations, but that's less than the number of unknowns that you have that appear then in your equations of equilibrium. And so we know from algebra that just does not work. You can't have more unknowns than the number of equations. And so that's then statically indeterminate. And so we need to we need deformation equations to achieve the same number of equations as the unknowns. And so those are again referred to as compatibility equations. When we get along further into the semester, when we talk about beams, they'll be referred to as continuity conditions, but those also refer to that compatibility type of condition. They're just called continuity conditions. And in those instances, as you look along the length of the beam, you can't have at one point displacement, say of 5 millimeters, say on the left-hand side of the point, and 10 millimeters on the right-hand side of the point. They both have to be the same value at that given point. And so you need a nice flow of that displacement curve to maintain continuity within the length of that beam. The same is true for the slope. The slope is going to vary with respect to that x position, but you can't have an abrupt change in slope. And so here's a statically indeterminate example where we're given a 7.5 inch. So this is the second member here that we're talking about, and then 7.5 inch deep into the page and 20 inch high oak. Young's modulus 1800 KSI. This block is being reinforced by 2 steel plates that are 2 inches wide, 7.5 inches deep, and 20 inches tall. So it's kind of sandwiched between the two. And if load P is applied to the top, 700 kip, what we're asked to find is the normal stress in each member and then the shortening of the entire assembly. And so with this one, we can draw a free body diagram. And there's a couple ways to draw the free body diagram. And so this is the way I just did it. And I'll talk about the other way that could view it too. But we have a rigid cap placed on the top, and that's just going to press down all 3 members. With this one, I did a sleight of hand difference with drawing the free body diagram. I know this thing is being pressed down and it's in compression. And so instead of having to worry about signs, I just drew the free body diagram so that the arrows are facing in for each one of those sections, with making that assumption that the members are going to be in compression based on the loading. What that does for you is it really takes the sign issue out of your analysis, and you don't have to keep track of the sign. And so that's just a little trick I learned back in the day to kind of help out with that process if you're 100% confident on the sign of what's coming out there. So the other thing is that P2 is the force of the oak, the force that it's supporting, and then P1 is the total force carried by the steel. And so the way I did this was half of P1, so P1 over 2 for each one of these. And I'll show you the alternative way. You could just look at that as P1 on each one of those. But if we were to do a summation of forces on this in the y direction, I didn't do that here. But if we were to sum forces in the y direction, we'd have these combined together to give us a P1 plus P2 minus P is equal to 0. P is given 700 kip, but we'd have 2 unknowns, P1 and P2, in that summation of forces in the y direction. And so we kind of see from equilibrium alone that we have one equation and two unknowns, P1 and P2. So we don't have enough to be able to solve that with equilibrium alone. And so we have to make use of compatibility. And so delta 1, the displacement we get out of the steel would be equal to P1 L1 over E1 A1. And the displacement we get from the oak would be equal to P2 L2 over E2 A2. And so for compatibility to be satisfied, we know that the displacement of the steel would have to be equal to the displacement of the oak. And that's then now our second equation that we have in addition to equilibrium. That'll give us two equations, two unknowns. And so with that, essentially what I'm doing here is looking at those members combined. But if we do that substitution in, we'd have P1 L1 over E1 A1 is equal to P2 L2 over E2 A2. And we can solve for P2 as a function of P1 and all the material properties and geometry properties. And then equilibrium, again, we mentioned that P1 plus P2 would equal to P. And so that gives us our second equation. And with that, then we can make that substitution in for P2. So P1 plus L1 E2 A2 over E1 A1 L2 times P1 is equal to P, and we now have it as one equation, one unknown, where we can solve for P1. And so with that, L1 is equal to L2, so those will cancel. And A2, the cross-sectional area of the yoke is 7.5 by 7.5, so 56.25 inches squared. And A1, again, this is the total area of the steel. So 2 inches by 7.5 inches would give us one of those plates, times 2 would give us the other to give us 30 inches squared total. And so when you then plug all those in to your relationship, you then have one equation, one unknown to solve for that. And with that, I'm just pulling P1 out of each one of those expressions. So we end up with P1 outside, and then it's just 1 plus the remaining values that we've indicated already. And that'll allow us to solve for P1. That'll come out as a positive 627 kip, but based on the direction we drew the free body diagram, we know that's in compression. And I think that's the main benefit you receive from that initial assumption that those members were in compression is you didn't have to worry about signs as you're going through your equilibrium and compatibility relations. Once you know P1, 627 kip in compression, you can solve P2 with, again, this relationship right here. We know P1, we can just solve P2 directly from that. And that is 73 kip in compression. And so the interesting thing, the Young's modulus of the wood was 1800 KSI. The Young's modulus of steel is 29,000 KSI. And so what we find when materials are constrained through compatibility like this, where they have to have an equal displacement or something like that, what we find is that the rigid material tends to be the load carrying member. They support the majority of the load, and the other one is just kind of along for the ride in that process, and carries much less of a load in that process. Once we know the internal loadings of each of those sections, we can calculate the stress. And so P1, the total load supported by the steel is 627 kip. The total area of the steel is 30 inches squared. Will give us 20.9 KSI in compression. And sigma 2 is equal to P2 over A2, 73 kip over 56.25 inches squared. Will give us 1.30 KSI in compression. And also just kind of note that the magnitudes of these in regard to failure, the factors of safety, that's something you need to look at because the yield or ultimate strength of one material might be much lower than the other. So even though steel is supporting more stress here, it may even have a higher factor of safety than the wood, just depending on its yield or ultimate strength. And so the way that we did this, again, we looked at that P1 as the total load and A1 as the total area of the steel. If you're to look at those instead of P1 divided by 2 and just say, well, look, we have a P1 on each side, all that would do is divide each of these values by 2. So we'd have half of the load being carried by each member. And then we'd have just the area of each member, so 15 inches squared. And so you would end up with the same stress coming out 20.9 KSI with that if you were to have drawn the free body diagram in that manner. We'll discuss that as we get further down. Then to figure out the displacement, all we have to do is take our solution, P2, 73 kip, and solve its displacement, P2L2 over E2A2. And we find that that displacement is 0.0144 inches down. And this is really the sleight of hand trick, or really the check that you can do to just verify you did the analysis correctly. When doing statically indeterminate problems, it can be easy to make a mistake and sign along the way. And so we have our compatibility constraint that the displacement of the steel has to equal the displacement of the wood. So let's just check that and figure out what the displacement of the steel is. P1L1 over E1A1 and 627 kip, 20 inches, 29,000 KSI, and 30 inches squared will give us the same displacement, 0.0144 inches. And so that was something I commonly did on the homework and the exams when I took ME 316, is that when we had these statically indeterminate problems, even though I found the answer, I checked to make sure that that satisfied compatibility by checking the other material as well, the other member. And then if those come out to be the same, you're really confident then that your statically indeterminate solution is correct. If they come out as different, then it's a big red flag that you've made a mistake in algebra somewhere along the way. And so this is the other free body diagram that I was mentioned that you could have drawn in this manner, where P is acting down, and instead of just saying that it's the total force of the steel, you could say it's the force in each segment of steel or in each side. So P1 would be half the total force carried by the steel. And so in that situation, you're looking at those individual areas, 15 inches squared, and equilibrium, you'd have 2P1 plus P2 is equal to P. And that solution process would follow the same. When you go through and solve for your displacement, then again, you'd be doing that for each member. So what you would find is that in this instance, P1 would be half this value, and the A1 would be half this value. So dividing both of those by 2, you still end up with the same quantity. So there are multiple ways to draw that free body diagram and how you want to define those values. Any questions there?
No.
And so next we can look into statically indeterminate with thermal effects. And here we have a 3-inch diameter aluminum alloy. Young's modulus and Poisson's ratio given, along with coefficient of thermal expansion, and then a 4-inch diameter steel, same things provided. And in this initial state, the end supports are rigid and the bar is stress-free at 0 degrees Fahrenheit. What we want to find is the normal stress in each bar at 80 degrees Fahrenheit, and really also the change in diameter of the steel bar and this displacement of the rigid plate. And so this gets to be a little complicated. I gave you a couple different solution processes for this to look at that. But first thing you really need to know is just what is that cross-sectional area of each one, pi d squared over 4. So we can solve those out and have the areas. I guess there's two different ways to tackle this. One is with 3D Hooke's law, and looking at the strain in the x direction is equal to 1 over epsilon times sigma x minus nu, sigma y plus sigma z plus alpha delta t. Only way sigma y and sigma z 0 if they're not constrained by these rigid sides. They're allowed to expand or contract if needed, and that it's a frictionless type surface between that contact. But in that regard, those states of stress would be 0, and that would give us sigma x is equal to epsilon x times the Young's modulus minus alpha delta t times E. And again, sigma x is equal to P over A. What we would find if we did a free body diagram is that the internal force is going to be the same throughout. So P1 is equal to P2. And so with that, sigma, again, P over A would give us epsilon 1 E1 minus alpha 1 alpha delta T E1. And then same thing for the second one, P over A2 would give us epsilon 2 E2 minus alpha 2 delta T E2. So we'd have that set up for each one of the segments. In this situation, we have several unknowns. We would have the load, the internal load being unknown, as well as epsilon 1 and epsilon 2. So we have 2 equations and 3 unknowns. And so we need a third equation from compatibility. And again, we're talking about that kind of epic struggle between aluminum and steel here. And so both of these really want to expand when the temperature increases. And so since they're placed between these rigid supports, they're not able to expand as they would wish. And so essentially, they're going to be in a struggle to find equilibrium where that internal force is the same between the two. And so that plate is going to shift to the left or the right based on that. And so with that, one of the displacements will be positive and the other one will be negative, the same value. And so delta 1 plus delta 2 would have to be equal to 0, which tells you that they're equal and opposite in sign. With that, just epsilon 1 would be delta 1 over L1, epsilon 2 would be delta 2 over L2. And so we have epsilon 1 L1 is equal to epsilon 2 L2, which would give us a third equation. And so you can solve the three equations, three unknowns, and determine P epsilon 1 and epsilon 2. But I advise an easier method to do these types of problems. It's a little bit easier to do the analysis as if the right rigid wall were not there, and to calculate, well, how much would these want to expand? What would be the overall displacement for those two combined? And then based on that, what load P would be required to push that entire assembly back to the rigid wall? That would be the P value that we're after. And so there, with that solution method, instead of solving three equations, three unknowns, you can kind of break it down into more of a solution process method, where you can look at those effects individually. And so the thermal expansion would be alpha delta T times L. And so the displacement then would be the sum of both of those, alpha delta T times L for the aluminum plus alpha delta T times L times the steel. And so these values are all known. And we can solve for delta directly. And then based on that, we have then the mechanical displacement. That would have to be the same combined. So looking at that compressive force going through PL over EA for the aluminum plus PL over EA for the steel would have to equal that same displacement. And we have the Young's modulus value of each A and L. We know that the loads are the same within each one. So this delta, we can solve the value here, and we then have one equation and one unknown. We're solving for P in the second one. And so for this statically indeterminate situation involving thermal stresses, instead of solving a system of three equations, three unknowns, we can solve one equation by itself, get a value out, and then solve the second equation, one equation, one unknown there, which is an easier solution method. And so going forward with that easier solution method, you can really kind of combine all that stuff. I would almost recommend doing that in separate steps, where you solve for this delta first and then solve the second one. I've kind of combined everything together into that process, which makes that a little bit more difficult to see. But then doing that, you just find that P is equal to minus 89.4 kip. And so that's the compressive force that is present in each one of those materials. And we can then solve the stress in each material, just the force divided by the cross-sectional area that we solved earlier. And so sigma 1 of the, of the aluminum is minus 12.65 KSI, and sigma 2 of the steel is minus 7.12 KSI. And then finally, when we're looking at the displacement then, if we were to look at strain 2 in the X direction, again, it would be E strain in X. We rearranged this, didn't we? So if we look at this relationship here, we move that to the other side. So sigma X plus alpha delta T times E, divide through by E, BS sigma X over E plus alpha delta T. So what we have here, that's where that came from. And so we have a minus 7.12 for the steel divided by its Young's modulus plus the alpha value that was given times the delta T will give us then the strain 2.9 times 10 to the minus 4th inch per inch. We weren't asked to solve what the strain in the Y direction would be, but you could definitely do that as well. I think we were asked to do that, looking at the change in diameter. So yeah, the change in diameter is a function of the strain in the Y direction. So same thing using Hooke's law for that purpose to solve the strain in the Y direction, and that would be equal to delta D over D. And the diameter was 4 inches, so that'll give us a change in diameter of 2.4 times 10 to the minus 3rd inch. This delta D over D, for example, when you look at, say, the circumference of that, the circumference is 2 pi times the diameter. And so when you do that analysis on the strain, that final diameter minus the original diameter, and place all your 2 pi's in there, all those, or pi times diameter, all those pi's will cancel out and it'll be left with delta D over D. So circumference is pi times diameter, and all the pi's would just cancel out as you do that. So that gets you the change in diameter. E2x would give you sigma x over L2 will give you 2.9 times 10 to the minus 4th. We solve that for the strain. The length will give us then a delta x of 5.814 times 10 to the minus 3rd inch. So the displacement of that steel section then is 5.814 times 10 to the minus 3rd, which means that's the displacement of that rigid segment between the two. If you were to do the same thing for the aluminum, you would find that that's also equal to 5.814 times 10 to the minus 3rd, but it would be in compression. They're both in compression, but as this moves to the left, the aluminum would also be moving to the left. The other way that you could do this step is delta x would be equal to the thermal expansion that you had minus then the mechanical displacement back. And so that would be another way to solve for that instead of looking at strain. So delta x would be equal to alpha delta T times L for the thermal expansion minus PL over EA for the mechanical compression that's being placed on there. And so that's, I think this would probably be more commonly how I used to solve those things. I just kind of wanted to show you that from the Hooke's law standpoint as well. But that would be something I'd recommend you to do, would just be do the math on that, where delta T is alpha delta T times L, and displacement due to the load is PL over EA. And with that, you're just putting the magnitude of P in there. Since I've set up the signs already for that purpose. But that really kind of covers chapter 4 from the perspective of looking at that relationship for delta, for constant cross-section, PL over EA, and then looking really at the effects of thermal loading as well. So I guess with that, are there any final questions? And so what we have then is the homework that's due for next Saturday. That's really all the review material that we've covered this week so far. And so the strategy that I would recommend is really to try to do that homework over this current weekend, so that if you have any questions, you could bring those up next week during class. Feel free to email me any questions too. If you're not able to join in on the live lecture, when I get those emails, I can just address those questions to the class during the live lecture, and you'll be able to see those answers later in the day when you review the live video. And then otherwise, if you're joining in, just feel free to ask those questions when you're here. And so that's it for today. And the main reason that I recommend that you do the homework this weekend as well is this content is really kind of something we've just recently lectured over. So it's a little bit easier to do those homework problems now than to wait a week when we've then talked for a week about torsion. And so by the end of next week, we'll assign the torsion problems, and that would set you up well for doing the torsion problems next weekend. So that's the strategy I would take in moving forward with that. Because one thing I did see, I was looking at the survey results for how many classes students are taking. At the time, there was a large number of students taking 3 classes this summer. And so you really need to manage your time effectively to juggle all 3 of those if you're doing homework. The thing I mentioned on Monday, kind of anticipate about 20 hours a week per your 3 credit class. So if you're taking 3 classes, you're probably looking at about 60 hours a week in doing homework and stuff like that here over the shorter summer semester. But I think we'll call that good. Are there any final questions?
No, I don't have any questions.
All right, thanks, Jordan. And so I think we'll call that good then, and we'll see you on Monday. Thanks for your time. Have a good weekend.
Thank you. You too.